Okay, good morning everyone. Today we are going to continue talking about OpenGL and GLFW, how we compile and run OpenGL programs. If you have any questions, if you had any problems in trying to compile these programs, please you may ask your questions. I showed how we can do it on Windows by using MinGW. But installation of these GLFW and glue should be similar on Linux, or I also provided links on how to do that on Ubuntu, thanks to last year's post by one of your fellow students. So you can try those links with instructions to get yourself working environment to compile, to build OpenGL programs with GLFW and glue. The examples that I provide, so last time we had a problem in compiling things, and I was just unlucky in the sense that if I used, I mean, actually I had myself and how to compile file in one of the examples instead of, if I started with this texture example, there's this how to compile txt inside this folder, which I missed, which shows us we have to have this GDI32 also linked with it. So we got everything correct: glue32, GLFV3, GLFW3, OpenGL32, glue GLU32. So these are OpenGL related libraries, OpenGL utility function calls here in GLU32. So these two are OpenGL related. This one is the GLFW library, which is the window management and keyboard mouse event management API that is also cross-platform. And glue32 is the extension library for advanced OpenGL calls if you're going to have these shader-related, programmable shader-related codes. So this is how you would compile it on a command prompt with MinGW. Now, the examples I provide you with 4 examples here, and I then added additional examples which contain Martian rugs and Spotlight. And the Spotlight examples is nice in the sense that it actually uses the non-program, it uses the default forward rendering pipeline that is provided on our GPU. So if you take a look at, there are no fragment shaders here. If you go and take a look at this code, spotlight.c, it uses some deprecated OpenGL functions actually. For example, like the lighting is completely done by using OpenGL built-in light functions. We are not using anything on the programmable shader. We are declaring our normal data. Some of the vertex and normal data is sent not in terms of buffer objects, but they're just sent directly with function calls. Look at this, how many function calls we make here. It's really inefficient, by the way, to do it this way. We are going to also talk about those, but this is the immediate mode of trying to I guess it's immediate. Let me actually. We are going to talk about those today. There are a couple of different alternative ways in which you can send this geometry data, this vertex coordinates, the vertex attributes like the normal vectors with them or color information. There are different ways you can send this data to the GPU, and this one is the least efficient way. The next efficient way is to use vertex arrays, and then in which the data is still in the CPU memory, but you just send all of the data in one shot with just one function call. And the most efficient one is to use vertex buffer objects, in which you actually send the entire data to the GPU's memory, so that every time you're drawing it, you're not referring to, you don't send it at every frame. Even with vertex arrays, you're sending it every frame. By the way, look at this is 150 times 150. How much does it make? 150 times 150. 25,000. So 22,000. So at each frame, and if you look at this, this is actually in our loop, in our animation loop, where we run it for every frame. So every frame, I'm making 22,000 times. I mean, there are also 6 of these function calls. 6 times 22,000, look, around 100,000 function calls to send. These are function calls, as you can see. Activations records are created to send the vertex data for one vertex. I'm making a function call, and this is in total. Actually, it's more than that. So it's not 150. It runs for 300 times. So 300 times 300, 90,000. So it's a lot of function calls basically, but this is using an inefficient way to do that. But even with that, I want to show you how efficient OpenGL, your graphics cards are, and see with these functions are executed on the CPU. But there may be some optimizations, I don't know, because it's really, as you're going to see, it's really smooth. Actually, it's using the vertex array object. Oh, okay. These triangles, which has a fixed normal here, 0, 1, 0. Actually, these are just used to draw the table surface. I'm going to compile and run this program, but this is just for table surface. In order to see the effect of lighting, spotlight in detail on a flat table surface, this is a subdivision. Basically, we subdivide this table surface into a regular grid of very small triangles. The table is actually a 300 by 300 square, the tabletop. That 300 by 300 square is divided into 1 centimeter by 1 centimeter small triangles. So these give me 2 triangles. Every small patch of grid cell, which is 1 centimeter by 1 centimeter, is like a regular grid, which is a cell, which is a square, and it's just drawn by 2 triangles for that square. So this is just for the tabletop, and the actual object, the lamp object, there is a table lamp that we render here. Those table lamp vertices are actually sent to the GPU by using the second most efficient mechanism with the help of these vertex arrays. So with one function call here, the draw elements, we render the entire set of triangles, which are referred to as in this. Actually, it's using vertex buffer objects, not vertex array objects. So here we are sending, but actually, yeah, let's see, vertex. It uses vertex buffer objects, but it sends the data every time. Yeah, so this GL draw elements, it's actually referring to the data that is in the GPU, but we are sending it, or are we sending it every frame? Let me see. At least that shouldn't be sent every frame. I think it is sending. So there are some inefficiencies in these codes. They are not the optimum versions, but this part is the immediate mode of rendering the triangles is the least inefficient way. So this one, sometimes we are able to send the entire set of vertex data or their normal data, this vertex pointer, normal pointer. So these are sent as a buffer. The entire set of objects are vertices are sent in one shot. Okay, so this quad is something that shows the lighting in OpenGL does not actually produce shadows. Light penetrates everything. It's like the interaction between objects and light is done without considering any possible objects that lie in between the light source and the objects. That's why I put this quad underneath the lamp to show that the table top is not going to be affected by that. But this is a simple program. I mean, it's 350 lines of code, but this will be a nice program which shows you how to use the fixed forward rendering pipeline. It has lots of keyboard interactions, as you can see. The process normal keys, a lot of keys, Q, A, P, L, T, G. So let's try all those. I'm just going to try to type on my keyboard some random keys to see what they're doing. It's difficult to memorize all these keyboard combinations to interact with the program, but let's try it out. Okay, so it's not using any, as I said, any programmable shader. So it's using the fixed forward rendering pipeline provided by OpenGL, and it runs on the GPU. Okay, so let's see what it does. So it's rotating something cam angle. So it should provide some rotation, but let's see. Let's try to compile it. So here is, let's go to desktop. These are examples 2, I guess. Spotlight. So the spotlight.c. So spotlight.c, first glue 32 GLF minus L GLFW3 and minus L OpenGL 32 minus L GLU32 and minus L GDI32. LGDI32. So it compiled with no problem, as you can see. Let me run it. By the way, you can run it here, or you can just run it by double-clicking on it from the browser window. So if we run it, so as you can see, that angle that we had here, it's actually providing a smooth animation. So what you're seeing here is a table lamp. By the way, this is really the table lamp that is colored in 2 different colors is just by coincidence that it's such a nice separation of 2 colors. It's actually what it's doing in this program is it's rendering the first 1/3 of the triangles with this color, RGB. So this bluish color draws the first 1/3 of the triangles, and the second 2/3 of the triangles are drawn with this reddish color. So this GL color tree, if the color property, for example, is just sets up some global color variable that the fixed forward rendering pipeline uses. So, for example, if I just change this part and get rid of this one, and I say here total number of triangles times 3. So here actually we sent the number of vertices. So when we are saying GL draw elements, GL triangles, the second parameter here is the number of vertices that are going to be drawn. Okay, so that's why the entire set of the table, the number of vertices in my table lamp is total number of triangles times 3. So the first 1/3 of it is that one divided by 3, which is this. The second 2/3 of it is uses this many vertices, and it starts actually, and this last parameter gives where should we start in the array. What is the first starting vertex in that array? This one says start at the beginning. Okay, it's not a pointer, but it's just how many. What is the offset that you're going to start with? So, for example, when I do this, the table, the entire lamp is going to be drawn in one shot. So let me see, let's compile this. So it compiled when I say spotlight again. As you can see, now it's totally blue. Okay, so these 2 coloring effect was just using, by the way, when I resize my window, as you can see, the viewports are nicely resized, and the aspect ratios are nicely maintained, depending on, for example, when I do it like this, it's changing the perspective view so that we are seeing a wider field of view. So this is actually done in code. If you inspect the code, it's not just squishing the scene. It's actually changing our field of view, our perspective, so that the lamp is always seen like this. Okay, I think that 2-color version was better, so I'm going to go back to that one. So the first 1/3 of the triangles, this color, the second part, the second 2/3 of the triangles in this reddish color. Let me compile it again. So this is how I usually do it. I mean, I edit my code in Notepad++. I use command prop to compile, recompile it. I'm not using an IDE. You can also use an IDE to do these things, building your program and do things like that within the IDE. But let me try to interact with this program. So where's our spotlight? So there are a couple, here's our spotlight. Actually, this clicking one, there is a global directional light, I guess, in the scene, in which by pressing one, I can turn it on and off, okay? So this is my spotlight that you see here, which is actually, the light is positioned here, directing here, but the light source itself is not seen as a bright spot in OpenGL. Light objects are virtual objects in which we only see their effects on the surfaces. If you have a light source in the environment, you don't see it as a light bulb, as a bright spot. That light source, as I said, is like a virtual object. There is no physical object related to this light source. We just see the effect of that light source on the objects, surrounding objects here. And we see here a nice smooth boundary of this light source because of my this tabletop is composed of like 90,000 triangles right now. They're all same color, but there are actually 90,000 triangles here. We could have just rendered them in random colors, which would make it really interesting. But you can try to modify these programs. So let's try some of these keyboard bindings. Yeah. So when I move the lamp, my light source is also attached to the lamp. So you can move it left and right. You should be able to do some other things too. Let me try. Yeah, actually, I'm changing some parameters of the spotlight. I think the boundary of the spotlight can be changed, as you can see. And at some point, we see a certain boundary which shows there's actually a strict cutoff of the spotlight in OpenGL, in which if this strict cutoff oh, why do we have this many triangles on the table? A very good question. That is related to how the fixed forward rendering pipeline uses Gouraud shading for illumination for shading the table surfaces, which means that it computes color per vertex of triangle, and the points inside the triangle, their colors are computed only as an interpolation of the vertex colors that are computed there. So when I have this spotlight, by the way, I can move it up and down with E and D. E and D moves it up and down, as you can see. Now, here's an example of Z fighting. At some point, we're seeing some effects of Z fighting there, but it's not. Going up and down is not that strict enough. So you can change the angle of your spotlight. That's T and G. And there was some other thing in which I can actually change. I don't know which parameters were those. I can change the cutoff value of this spotlight nicely. Oh, I think it's this one. Yeah, this one is good. So you can set the cutoff value in such a way that you don't see the boundary at some point. It makes it nice. So by the way, we can move our rotating camera up and down like this. So let me get back to your question. If we had only two triangles on this table, which is a square, what would happen is that I would not be able to see the effect of this lighting on the table, because when we compute the color, when this lighting is taken into effect to compute the color of a vertex, when we compute them for these corners of this large table, as you can see at this moment, the colors of these corners are completely gray. They are not affected by the light source. Therefore, I will not see the effect of the spotlight on this particular spot on the table, because that part on the table will be computed as a interpolation of the four vertices, which are not affected by the spotlight at all at this moment. Okay, so in order to have this nice smooth spotlight effect on the table, what I do is I divide this division, 90,000 triangles is a lot of triangles. Therefore, if you look at the illumination on the tabletop, it looks really smooth. I mean, it really looks looks like we have a smooth spotlight there. Okay, we could have used, actually, instead of having 90,000 triangles like this, we could have written our own programmable shader in which we don't compute the color as an interpolation of the colors computed at vertices. That's a different shader called Phong shader, or normal interpolation shader, in which instead of having computing color for the vertices and interpolating them, we could have computed use this basic elimination model. We can execute it for every fragment of these triangles individually when we do write our programmable shader, and in that case we wouldn't need 90,000 triangles, and it is possible to do that in programmable shaders. OpenGL does not provide that. The default OpenGL does not provide you this normal interpolation, or does not allow you to compute color shading model for every fragment here. It only allows computation of colors at the boundaries and interpolation of them. This is called smooth shading in OpenGL terminology. But yeah, we could have done our own shader and compute color per fragment here, and it's done like this. I actually showed you that piece of code previously. Let me show you that part here. So here I have some shader examples that I showed you before. I think it was in 2003. Yeah, shaders. So there's here fragment Phong and vertex Phong. So these Phong subscripted Phong files, VS stands for vertex shader. If you go here, it's using it's transforming the vertex, and it also computes these three variables: the normal vector, the to light vector from a point, and the position in the world coordinates. So when we do model view projection matrix of a vertex, the position of the vertex is is transformed into the viewport coordinates. It's projected. But in order to do lighting computations, I need the transform coordinates of that point in this camera space. So that in other words, I need to also have the XYZ position of a fragment in the 3D world coordinate system without doing projection. So this is how I do. As you can see, if you just multiply it with GL model view matrix, this gives you your position in the camera space. And by declaring these three variables as varying variables, in my fragment shader, I make sure that these are going to be interpolated for every fragment. So this position actually is the position of the vertex of a triangle. But when I'm computing the lighting, I need the specific position of a point inside the triangle, and that's done by interpolation too. So I'm going to come back to your question, but if you look at this Phong shading part, it just uses this normal vector, to light vector, position vector that is automatically interpolated by the GPU at this point. In this fragment shader, you do not deal with vertices of your triangles. You're actually writing code per fragment of a triangle, per pixel of a triangle, and this is how you initiate how you execute your basic elimination model, in which you compute an ambient color, the specular component, the diffuse component. If you look at these, we normalized our vectors. We compute the health vector like this. We have the health vector, and we have the to light. So if you look at this, we can do the dot product between the light vector and the normal vector of the surface. This is the diffuse model. You just take the dot product, and you take, if the dot product is negative, you just want to treat it as 0. You use this max functions for that. You multiply it with the reflectance, diffuse reflectance coefficients of your triangle, which is using the OpenGL global variable for that, in which you can use GL material functions to specify a material before you draw an object. These are not attached to objects. OpenGL is not object-oriented at all. It's just like a paint program in which you have some global current settings. For example, before drawing something, you just said, this is the material I set globally. And when you draw the object, it's the material that is being used for that object. So this is the light source's diffuse intensity value. So multiply all these things, you get the diffuse component. This is your specular reflection, in which you take the power of front material shininess. This is the specular exponent. So you compute specular with this, again multiplying, taking the dot product of your normal vector with the half vector. So this is everything we have seen in class turned into this simple only like 20 lines of GLSL code. You just add them together, and if the result is larger than 1.0, you clamp it to 1.0, and you don't want it to be negative as well. The smallest it's going to be 0, and you just set the color to this one. So this provides a way to compute color per fragment. And other programs, I mean, this Fong shader, Unity is implemented in Unity by default probably, or other programs like Blender, when they are rendering these things, they are using. So this Fong shader, which wasn't standard in OpenGL in 2000s, actually now with the help of programmable shaders, it has become a standard. So you can actually use normal interpolated, because as you can see, the interpolated thing is the normal. It's not, there's no color coming to this fragment. Color is computed within for the fragment. Yeah, you can achieve similar lighting in Blender because it uses probably not that Gouraud shading part, which is color interpolation. It computes color per fragment. So it's still running in the background. But as you can see, all these, even with the inefficient version, I think the animation is pretty smooth. Because, for example, I can the keyboard interaction, when I take my camera up and down, changing the position of the lamp, things like that. I mean, it seems pretty smooth. As you can see, there are no shadows. I put this purple small square is actually underneath the light source, but it doesn't produce any shadow on the on the tabletop. So there are no shadows in OpenGL. So let's also take a look at another example, and I'm going to go back to slides in the last 20 minutes. So if you go to Marty and Ruck's example, we have a lot of things here. By the way, if you go to this folder, the Spotlight, so the entire geometry of that lamp is in this file format named tablelamp.tree. So this tree, I think, is like a polygon. Actually, it's a very, it doesn't have any header or anything. It's our index face format. So what we have here are 6 values per vertex. These are normal vectors, so that we get nice smooth shading on the lamp. So these are normal vectors, and these are vertices. So I have a list of vertices for the lamp along with their associated normal vectors. Are these normal vectors? Yeah, they're normal vectors, but they're not normalized. As you can see, their length is maybe smaller or larger than 1. But I believe they're normal vectors. If I go back and take a look at the code here, Spotlight, the place where I read the lamp, where do I read it? Initial. Yeah, in init scene. So there I have an init scene function somewhere here. Oh yeah, the data of the vertices of that lamp is sent actually here with it's done with the most efficient way of sending data, called vertex buffer objects. Okay, so here we have the vertex data. The second floating values are the normal data. Okay, so these are so all those 6 values per line, they are the associated vertex attributes, the coordinates of the vertex and the normal vectors associated with that vertex. And then after that, if you go to this one, at the top, I don't have any number of vertices associated with it. I think that's just, I hard-coded it here. Total number of vertices, how many of them? Total number of vertices, I think that's hard-coded. Yeah, look at this, there are this many, 1,500 vertices. I should have written in that. So it's very bad coding. In the file format, for example, I don't have this. This program will only work for this particular lamp with 1500 vertices, and there are exactly 3000 triangles. Okay, so it reads 3000 triangles after that, and it reads the triangles in such a way that, so yeah, after 1500 something, as you can see, that's exactly this many. I just read the indices, so it's index. So these vertex number 4, 6, 1 makes this triangle. So it's similar to that poly format MeshLab uses, and there are 3000, exactly 3000 triangles in this table lamp. Okay, so the other example, Marty and the rugs, has lots of things here. There are some textures: Marty texture, rug texture, mold texture. So there are 3 texture images, and there is a fragment shader, and let's see what this fragment shader is. It just uses the texture. It doesn't compute any color. It's just for texture mapping, and whatever the texture color is, we just retrieve it from our texture map, and the fragment color is assigned to that texture color. So there is no color computation, there's no lighting in this example. It's just an example of how we can map and get a texture image and assign the texture image color directly onto the surface of this object. So that's our fragment shader basically in this one. And if you look at the vertex shader, it's also doing something really standard. It gives a model view projection matrix from the OpenGL. You're not using the built-in variable. It's transforms. It does the basic vertex processing stuff, multiplies our original vertex data, vertex coordinate, with this model view projection matrix, and it also finds. So this normal, it interpolates actually normals, but they're not used actually. I think in one version of this one, the normal was used, but as you can see, it's not used at all. So it's again doing things that are redundant and not used at all. So this normal vector here, or the position, is not used at all. So we could have used these to compute some kind of a color and blend it maybe with the texture coordinate, but these are not used at all. So I can safely delete these. They're not used. And so this position and normal, I'm not using those, so I don't need to have these. But I have the texture coordinates assigned, which I use in the fragment shader. As you can see, the texture coordinate, which is the interpolated texture coordinate within the triangle, will be used. So I just deleted normal and the other. By the way, making changes on your vertex and fragment shader, you don't need to recompile your CPU programs, because this vertex shader and fragment shader is read by our CPU side program, this render.c. So it reads this vertex shader. Let's see where they are. Let me just try to, probably it's also hard-coded here. Yeah, as you can see, it opens and reads these files during runtime, and then compiles those shaders and loads them onto the GPU at runtime, which is going to do this texture mapping thing. By the way, we can also do texture mapping by using default OpenGL functions too, but this shows you an example how you can play with your texture mapping at if you're writing your own fragment shader. So these are really nice examples. If you can use them as templates when you're developing your code. Okay, how to read a texture from a PPM file, for example. This one, this load texture ASCII, reads a PPM file and loads it in memory, and sends this by using these OpenGL functions, sends it on to GPU for doing texture mapping. As you can see, after you send your entire large megapixel texture image onto the GPU, you can just free your CPU memory. You don't need to store the image pixel values on the CPU memory. You can, after you send this, at this point, this GL text image 2D function makes the copying of your texture image to GPU memory. So how does it look like when I compile it? there's also we also have the models. This Marty and Rux TXT is the geometry. The PPMs are the textures. So if you look at the geometry information, Martian texture, right? It's not only geometry, there are also texture coordinates assigned to vertices. Yeah, so these are my vertices. This one nicely has the number of vertices at the top. So these are the coordinates, three-dimensional coordinates. And at some point I should have, yeah, two-dimensional UV texture coordinates for those vertices. And these are the triangles vertex indices they make. And there are actually three models here, one for our zebra and two for the rugs. So there are two rugs around our zebra from the movie Madagascar. So let me compile it. Render that. Oh, let me just how to compile. So I just need to copy and paste this because it's the same file name, render.c. So I compiled it. So when I execute it, Martian texture, oh no, render, the name of my executable is render. So it's this. Yeah, this is our nicely texture mapped zebra, which is now in this case, in this program, for example, when I'm resizing the window, as you can see, I'm not changing my perspective as in the spotlight. You can see those different differences, what happens when we do resize. This one just changes the viewport probably without taking into the aspect ratio, changing the perspective matrix. And therefore, when you make resizing, as you can see, you distort your image. Either you can get a fat Marty or a thin Marty, whatever you wish. So, okay, like this. So, but this is, as you can see, there are three different textures mapped onto three different models here. And the texture coordinates are used to do the texture mapping. Again, it performs a simple, the dynamics of this animation is just we are rotating around, or our camera is rotating around this model. Or you may also think about the same thing. It's also always relative. All these rotations are relative. You may also think that the camera is just still, but the objects are rotating around some axis that pass through here. You can also think about it like that. And here are the some statistics about what we're doing. Our OpenGL version is using, so it was able to get the OpenGL version correctly, our renderer. And these are the textures we have read, how many pixels we have read from these textures. Okay, so just take a look at these programs. Oh, the flickering, that's a good point. We are going to talk about it on the slides. In order to have non-flickering, we use what is called double buffering. And GLFW API by default gives you Windows context, graphics context, which are already double buffered. You don't need to do anything about that. The only thing that you need to do is at some point at the end of your window here, so this one is actually not doing anything, so so the indentation is all off. So this one, gel swap buffers, is the function that you call to make this buffer switch so that we don't get this flickering effect. So this is what double buffering. You only need to say swap buffers at the end of your main. So this while loop, as I said, the indentation is off here. Probably it was edited in some other program. But if you look at this one, the while loop is our main animation loop. At the end of our main animation loop, we call these two functions, swap buffers to swap. After it's drawn, we can now swap the buffer to display it. And then the poll events is looking for keyboard events. If you want to exit the program, for example, by hitting the escape key. That's what the poll events does. Whether a key is pressed, a mouse is moved, a mouse is clicked, things like that happen in this GLFW. As you can see, all the function calls have these prefixes which indicate which library it's actually using. This glfw function calls are preceded with this prefix glfw, and this gl, the function calls that have this prefix gl are OpenGL function calls. Right, so we are going to talk about all of them in detail when we talk about programmable. We are going to talk about the GLSL language, some of the OpenGL function calls. We just now gave all these examples to you in one shot. Don't get overwhelmed with all these different functions and everything. It's just I just wanted to show you what kind of things you can do with these, but we are going to go into details of, for example, texture mapping, how we can do different things, advanced things. We are going to go step by step in all these to tell you how they work. Okay, don't, as I said, don't get overwhelmed with all these different libraries and functions. We are going to go step by step, and we're going to spend the next 3 weeks talking about these things. So hopefully you'll have an understanding of these concepts here. Okay, so if we quickly go over, we don't have much time left in today's lecture, but if some of these will be repetition of what I already just talked about. So if we go over them quickly, in order to open a window, we are using, as I said, this glfw window, glfw library. It uses an initialization. So first it has to look whether the graphics card or the operating system allows you to initialize a window. If that's not the case, you may exit with a failure signal. And you can also, while you're initializing your window, this window hint tells you what kind of an OpenGL version. Is it going to be 2.1? Or what kind of, there are different versions of this OpenGL and GLSL language. Certain versions are they're not sometimes backward compatible, so you can actually, while initializing your window, you can ask for a specific version supported by your GPU. And if you don't, sometimes this may cause a problem if that version is not supported. You may just also leave, I don't know whether these are mandatory. If you don't call about any major minor version here, the window hint, I think the currently available version is going to be used. But this is the function to create your window. You give the size of your window with the width and height, and you give it a title. The last two parameters we just give null. I don't know the details of all these functions, and you don't need to memorize. You can just refer to the API reference manual to understand the details of this. There's a nice documentation on glfw. If the window is not created, I mean, if this glfw create window returns null, it means that we weren't able to successfully create our window. We can just terminate the application again by signaling some failure. And after that, we make our current context this created window, which basically means that you can have an OpenGL application in which there are multiple glfw windows which are doing different things. For example, you can have maybe stereo vision by just moving your camera a little bit left and right, or moving left and right. You can have multiple windows. So there are some advanced functionalities of glfw which allows you to have multiple windows, full screen, all these things. You should look into the manual if you're going to professionally use glfw in your applications. So this double buffering, by default, glfw windows are double buffering. It's the mechanism that allows flickering or tearing. So this is tearing. In order to not to have this tearing, actually, this is an important function to call in your functions, the swap interval 1. Default interval is 0, which can cause swapping of the buffers in the middle of the monitor's refresh cycle. So this function is used to ensure that the buffer swapping occurs at the same time as the monitor is refreshed. This is called the vsync time, and I didn't know these before. This is one of the slides also just added by looking at the manual. I just had one template for a glfw example. I built all these examples by getting some code from that template. But it's good to know what these functions are doing, why you need them, why you use them. Yeah, there are in double buffering. There's a typo here. We render to a back buffer first, which is not directly shown to the user. After the drawing is complete, this GLFW swap buffers is going to directly do the swapping in very fastly, and therefore we are not going to do this flickering. There are two modes, windowed mode. If we have two different windows like this, we need to switch these pointers. And there's also an in-window mode. I mean, if we have a small window, we need to tell the graphics pointer which one is our current screen. And in the full screen mode, when you're having a full screen application, the video pointer directly is flipped in order to now show the other buffer that has been drawn and ready to display. I mean, in terms of programming, we don't. This is done automatically for us. I mean, in terms of coding your application, you don't need to know anything about double buffering at all. All you need to do is call this single function, and that's it. Okay, GL swap buffers window. The user interaction is done in an event-based mechanism. So when we call this poll events, first we have to set the keyboard callback functions and mouse button callback functions. There are other functions related to keyboard and mouse buttons. And these are their default value, how their signatures should look like. You can name it any function you want. Here is you give it the function name, which is basically a function pointer here, and you give your window. You're going to be listening those events within this window, and for example, there are some GLFW constants like this mouse button right. The mouse buttons are distinguished from left, middle, right, and the action, whether you have pressed it or whether you released it, things like that. At what kind of event, what happens? So you can have these different events, actions on the mouse or keyboards. Also, you can set a window size callback. When the window size changes, this callback function is automatically again called, and you can, for example, update your viewport with the width and height that is going to be automatically sent to this function when this event happens. So some of these input parameters, I mean, all these input parameters, after you register them, these input parameters are sent to these functions automatically by the event handler, whoever is generating that event. So I don't know what this scan code is, for example. I'm just using most of the time the key and action only. And there are different modes. So it's really an advanced way of handling keyboard functions. Maybe for special keys, we can, maybe they are using that regard. And this is, in GLFW, as I said, in a while loop, we have our infinite rendering loop. So in this infinite rendering loop, until the window closes, these are the main things we do. We render our scene by clearing everything, frame buffer, and drawing. So all these draw calls, drawing triangles, primitive by primitive, drawing the entire scene is done here in render scene. If you're doing certain changes, for example, the animate function may only be responsible about changing the current camera angle. Okay, you don't need to have it as a separate function. You can write everything, whatever you have in these functions, you can write them also inside this while loop. We can also, for example, show the current frames per second at the window title. I think I have an example of that too. If you need something like this, I may provide that example to you. And we swap the buffers and we poll for user events. After this window is closed, we destroy our window. There are probably some cleanup functions at this point. We terminate our program and exit success. There are some values here. Some documentation here at this GLFW website, which you can take a look at. There are other window managers. Before GLFW, 10 years ago, I think when I was a student here, GLUT was available back then. So GLUT is also very old, not maintained anymore, but it's very lightweight. API for window management. There's SDL, and there you can use Qt, VX widgets, X11, or other type of things as well. So it's a good place to stop here. We're going to continue on this next Tuesday. I'm going to show you these different, so this is the immediate mode, okay? And we're going to see how we can send them and to this geometry data, how we can draw objects on our frame by using OpenGL. Now we are going to go into details of OpenGL and continue talking about these examples on Tuesday next week. Happy New Year, everyone. I wish you Happy New Year. Saturday is the 1st of January. So I will see you on Tuesday next week. All right, do you have any questions? Okay, thank you very much. I will stop recording now.